Great. So welcome to the third class on the Branges spaces. In today's class, we will cover, I think it's chapter 5 and 6 of the book. And it's the first instance of a space of analytic functions you will see. And this space is actually connected with the Branges spaces, which we will see later. And it's entirely based on Poisson's representation for a function with no negative real part in the upper half plane. Okay, so it's a very nice and simple construction, and it's a nice example of a space of analytic functions. Okay, so what I will do something a bit different from the book. So to avoid some big formulas and to make things a bit clearer, because in the book it's just, I think the 2 chapters is just like 4 pages. Yeah. Okay. So let me define this LV spaces first. So let phi be some function from the upper half plane to the complex number, which is analytic. And let me just do something. I want to. Yeah, okay. Let me do that later. So it's analytic and has real part greater or equal to 0 in the upper half plane. Okay, great. So we know what the function is. So by theorem 4, we know that its real part has to be given by Poisson's representation of a measure in the upper half plane. So so the real part has to be given as a, this is called a convolution, if you wish, a convolution against the Poisson kernel, which is this guy here. It's the Poisson kernel, plus a linear factor. Okay, so this P here, greater or equal than 0. And then if you solve problem 5 at this point, so by problem 5, which is actually just a simple computation. If you use the formula for phi, which is also in theorem 4 and theorem 3, and you do this, then it's a simple computation, and you can show that this is equal to this thing here. If Z and W bar is in the upper half plane. Okay, so basically that's what we have. And so these are the things we know. And what we construct here is a space of analytic functions in the upper half plane, so that this guy here, it is its reproducing kernel. Okay, and I will explain that in a moment. Okay, so definition. Sorry, yes?
One small comment. I think in the first term, there's an I too much.
Yes, thanks. There is an I. Yeah, you're correct. Great. Yes. Okay, so the definition will be, so the definition of the L-phi space will be, so L-phi, what is it? Fancy L here. It will be just analytic functions on the F plane. And there exists some lambda complex number, and there exists some F belonging to the L2 space related with this measure mu, which is given by phi, is uniquely associated with phi. So that f of z equals lambda plus 1 over pi I. Yes. Okay, that's the definition of the L-phi space. Okay. So that's an explicit definition, and if you go to the book, it's not quite explicit the way he defines. So you can see this is a vector space. So if you add any functions, any two functions in this space, have another function in the space. However, you have to show that the definition is unique in the sense that, well, it could be the case that you can represent this function with a different lambda and a different little f, and then you get the same thing. So when you add two functions, say f plus g in the space, what you're doing is you're adding lambda plus, let's say, lambda f plus lambda g, and you're also adding the ft, the ft plus the gt. And this has to make sense because if you have two different representations, then it could be the case that even the addition doesn't make sense in the space. But it will. So, and I will explain that in a moment. Let me just define the norm in the space first. So the norm of the space, which is, we can put this subscript here or not, depending if I want to avoid a mess or not. So the norm will be basically just take the norm squared of the constant term, and you multiply by this factor, and then you just take the norm squared. Of the function little f with this L2 space here, okay? So that's the definition, and from the norm, you can easily guess what is the inner product we put here, okay? And the remark is the following, that this is well defined. So this is well defined. Why? Well, because suppose I write a g as f of z minus lambda, for instance, and so then the real part of g, I'm just removing the constant term, so the real part would just be given by this guy. So if I compute the real part, I get just a Poisson kernel. Okay, and then I can split f in its positive and minus its negative part, okay? So f plus would be just the maximum between f and 0, and f minus with the maximum between minus f and 0. And then I can define this measure here. So sorry, this non-decreasing function nu as the primitive of these guys. Okay. And then we know by theorem 3, which is a Poisson representation theorem, that that we have that the integral from a to b of f plus or minus t, the mu of t, which is simply just the integral from a to b of the nu plus or minus t. Okay, this is the limit when y goes to 0 of the integral from a to b of what? Of the real part of the function defined by f plus times the measure and f minus times the measure, which would be this guy here. Is supposed to be dx. Okay, and this holds whenever, and this holds whenever, this is whenever a and b are points of continuity of nu plus or nu minus. So this is A and B are continuity points of, let's say, both plus or minus, because, well, we know that the discontinuities are nu plus or nu minus, they're countable. So therefore, if it just take, let's say, the intersection, this is a everywhere dense set, for instance, so you can take A, B in any interval you like, basically. Okay, so that's what we know. So, so if we assume, so if G, say, which would be the case of f, is representable by another function, let's say f tilde, okay, then what we know is that, well, it has to be the case that, well, the plus part and the negative parts are the same, because, so it has to be the case that integral from a to b of f plus or minus t, by what we just did, okay, equal, because, well, they're equal. So I'm assuming that G has these other representations. So the same computations we did, everything we did up to this point applies. But then we get two different things. So, okay, if, and then if A, B are points of continuity of, let's say, nu plus, nu minus, and then nu tilde plus, which would be the guy coming from this, and nu tilde minus. Again, these are a bunch of them, because if you intersect all these sets, it's still everywhere it ends. But if that is true, then, well, they have to be the same. So this will imply that f plus or minus equals f plus or minus tilde. Okay, for each plus and each minus, but mu almost everywhere, because since we're multiplying by this measure mu, we have to be careful with that. But that's basically all we can ask, because we always have this measure. We always have this measure here. So the best we can ask is that they are equal mu almost everywhere, but that's enough, because then they will be equal as functions on L2, and that's how we define the space, okay? So the representation is unique for at least for the f. Then you can ask, well, maybe the lambda is different, but the lambda is uniquely defined in terms of f. So and then notice that let's say f of I minus say 1 over pi I integral of ft say t squared plus 1. Yes, I'm putting z equals I. Oh no, so it's just t minus I, sorry. Yes, so this is equals lambda, for instance. So lambda depends on just capital F and the small f. So if they are the same, then the lambda is the same. Okay. So everything is well defined. Any questions here? Okay. So basically, if you notice what we're doing, it's almost trivial that this is a Hilbert space, because basically what we're doing is just taking some map. In the case is this map here that takes some f and maps to this representation here. Okay. And then I'm adding a constant, but that's okay. Anyway, just taking a map and then just taking the range of this map and putting in the range of this map a certain norm that comes from the domain of this map, which is this guy. Okay, if the map is continuous, then it should be the case that you end up with a Hilbert space. Okay, in fact, the norm, if you see the norm inputting is exactly the norm, if you ignore this part, it's exactly the norm in this space. So this map here, which takes an f and takes it to this function capital F, will end up to be a unitary map because it's preserving the norm. So it's an isometric, it should be an isometric isomorphism. And that's what it will end up to be. Okay. So let me write the result. Okay, so this will be theorem 5, but I will split theorem 5 in 2 parts. So part 1, it's L phi is a Hilbert space. Well, we already know it's a norm space, well-defined vector space over the complex number which has a norm. And then we have to show that's a Hilbert space. So the norm is also a good norm in the sense that if the norm of f is 0, then f is 0, because if the norm of f is capital F is 0, then it implies that the little f has norm 0, so this is 0, and also lambda has to be 0, so lambda is 0, so then capital F is 0. So okay, so it's a decent norm. The only function with norm 0 is the 0 function. So here, really what we have to show is that the space is complete. Moreover, if we define kwz of phi, which I also often denote just as kw of z and forget about the phi. If we write it like this, define it like this, then kw belongs to L phi for every w in the upper half plane. And it acts as a reproducing kernel, and f of w equals f kw. And this is the inner product on the space, so L phi, for every f in L phi and for every W up. Okay. And then in particular, we will conclude that in particular, the functional, which is the map that takes an f in L phi and just maps to f of w. So you fix w in the upper plane, you fix that number, and then you consider the map, the functional that just takes an f in the space and maps into fw. Okay, so this will be a map that takes a function to a complex number. So the functional, which is called also, usually is called like the evaluation functional, because you're just evaluating the function in the point, is continuous. Okay, so moreover, if you define the map U that takes an f in L2 of mu, and that's the unitary part that I was talking about, and takes into this representation here, okay, so then U is isometric. Okay, so it takes, so it preserves the norm. In particular, if U of f is 0, then since we just saw that the only zero function has norm, the only function with norm 0 is the zero function. In particular, the kernel of U is trivial. So U is isometric, and the orthogonal complement of the range of U. So the range of U will be functions inside L phi, because this guy here belongs to L phi by definition. So the range, the orthogonal complement is just P times constant. Okay, in particular, if P is 0, then the orthogonal complement is empty, and therefore U is isometric isomorphism. So let me write that here. So if P is 0, then U is unitary, which is just another word of saying isometric, which is equal to say isometric isomorphism. Okay, so basically this is saying that the space L2 mu, if P is 0, then the space L2 mu and the L phi space are exactly the same, okay? I mean, that two Hilbert spaces which are separable can be exactly the same. That's kind of obvious. Is every Hilbert space with separable is the same as any other one. But the interesting thing is the map that takes one space to the other and preserves the norm. Okay. Any question in the statement here? Okay. So basically, we have some things to show. We have to show this a Hilbert space, and once we have it, then we have to show this identity here, which should be easy to show as well. And then in the end, we just have to notice. We just notice that this guy is an isometric isomorphism. If you really think about this, has to be the case, because the way the space is defined, well, is defined as the norm being exactly like this and functions that can be given like this. So it's almost trivial. And if P is 0, then you even don't have this part. So it's just have exactly, I mean, it's just like showing the obvious. But anyway, let's prove that. Okay, so what I would do, I would just deal with the case P equals 0. And I will leave you to fill the details with P greater than 0. Let's say you fill the gaps for P greater than 0. Okay. So let me show first that the space is complete. So for instance, suppose you have Fn is a Cauchy sequence. In L phi, okay? But then by the definition of the norm, this is exactly saying that if you take the little fn that represent each one of these capital N, this has to be is a Cauchy sequence in L2 of mu before it converges to some function in L2 of mu, because L2 of mu is complete. Okay, and therefore I can define, capital F just by taking this map U here, which is just writing it using this representation basically as U of F. And by definition is on, then F belongs to L phi, which is obvious, and then by the equality of the norms, by U being isometric, and then this implies that Fn converges to F and L phi. Okay, so that shows that the space is complete. Okay, it's just by them. It's kind of almost like just using the definition. Okay, so so by definition, so let me show now. So instead of dealing with the reproducing kernel for a moment, let me see. Yes, let me show that the map U, let me show this part here. Okay, that the map U is an isometric isomorphism. Whoa, okay. So we already know that by definition, I'm assuming P is 0. So by definition, if F belongs to L2, I do have a function by this representation. It has the same norm. So let me just say that it is almost, it is not almost, it is trivial to see that UF norm in L phi equals the norm of F in L2 of mu. So therefore it preserves the norm. So therefore it is isometric. And in particular, if I take, and what is the range of U? Well, by definition, I define the space as being the range of U. So of course, that's the, so is empty, of course. Okay, so another part which is trivial. So this was the first part, and this was the second part. So now we'll go to another part. So let me deal with this kernel thing. Okay, so now we go back to problem, problem 5. So the kernel, which is, let me rewrite again. By problem 5, we have a representation of this, and if you put p equals 0, then the representation becomes 1 over pi squared times integral from minus infinity to infinity of the mu t, and then you have t minus z and t minus w bar. And then what you see is that, well, you can just rewrite this in another way. You just erase this and you put 1 over pi I, and then you take this guy out and you put it here, oops, and you put it here, and then you put minus pi I t minus w bar. That's the same thing. So now you just realize that, so that implies that k phi, let me say just kw, is then u of what function? Well, the function is this guy here. It's just 1 over minus pi I t minus w bar. Okay. So therefore, by definition, so kw belongs to L phi for every w in the upper half plane. Okay, it's most trivial as well. Page here. And then now, well, okay, but we do have that. And so let me just compute the inner product. What would be the inner product of some capital F with kw? Well, by definition, that would be the integral from minus infinity to infinity of the little f that represents f, which is ft, and the little f that represents kw, but that's, we just computed, is 1 over minus pi I t minus w bar. But then I have to put bar in everything, and then d mu t. But then once I put bar in everything, you see that that's exactly the representation of f at the point w. So by definition, this is f at w. Okay, so this is by definition. Okay, and there we go. That finishes the proof.
I have a question.
Yes.
So we said that this L of phi is a Hilbert space, but I haven't really understood what the scalar product is that we use. We just use the scalar product on L2?
Yes, that's the whole point. The point is that what we're doing is just taking a map from one space to another, which is the map U, which we know has an empty kernel. And then we're just defining in its range the norm there as being the norm of a capital F, as being the norm of the little f.
Okay, okay, so we do the same. Yeah. Okay.
Yeah, so that's what's doing here. Like, yeah. This is like a standard procedure that if you see that the kind of proof we did here is just doesn't really use anything about phi being with no negative real part in the upper half plane. It's just a standard procedure. It's like when you have like a measure in a certain space, you pull back the measure from another space, push back the measure. It's kind of the same procedure, the same idea, let's say. You're just moving the norm to the other space. It's like, imagine it's like you have like L2 of the line, and then you have a certain basis, and then you just make an isometry between this space, L2 of the line, with the space of little L2 of sequences, where you just map the values of the coefficients and the expansion of the spaces on L2 of the line to the sequence of the coefficients. It's like the same thing. Great, so let me go to part two, and the part two is a bit more complicated, but not that much. Oh, but before that, I want to make a comment. Yes, so remark. So note that if L phi equals another space L phi tilde isometrically, so suppose you have L phi and you have L phi tilde and they are equal with the same norm, then phi equals phi tilde. What is to say that the measure that represents phi equals the measure that represents phi tilde. Okay, so let me show that. Yes, let me show that. And it's actually really easy. If you have two spaces with the same norm, okay, then the reproducing kernels, the KW, have to be the same. Okay, this is just abstract, but since we have a formula for them, actually, the KWZ is given in terms of phi, and that's just plain obvious. So we know that this has to be equal to that because we have a formula for them, and they depend on phi and phi tilde. Another way of showing this without even knowing a formula of k phi and k phi tilde, that's just using the inner product property that they reproduce a function. And then if you use the inner product, you show that this is true as well. Oh no, sorry, I was saying it was too fast. I'm assuming that the spaces are equal, not that the functions are equal. Okay, so we do have to make the computations. So why this is true? So I claim this is true. Okay, yes, sorry. So I claim this is true. So why this is true? Because, well, we have k phi of wz. So what is that? Well, that is just k phi of w. Let's put a dot here, and then k phi of z, and let's put a dot here. Okay, that's the inner product in any of these spaces because they are equal and they have the same inner product. That's the assumption. Okay. But I do also know that, well, if I consider this function here as a function in the L phi tilde, then this would also be true if I put tilde here. Because the phi tilde kernel reproduces any function in its own space. So I could definitely put this guy here. Okay. But then if you bar it, then if you do the most simple trick you can think of, just take the conjugate. Now inside the conjugate, you are taking the inner product of this guy against this kernel. So therefore, it has to be just this function evaluated at W. So this has to be k phi tilde of z at W, everything bar. Okay, but this equals k phi tilde. Well, by the formula of the phi tilde, you know that this is just W z. Okay, so now the kernels have to be the same. Okay, and so the proof here in this thing is just almost like a mental proof. You realize that you can use this inner product here in any of these spaces, so then you can put tilde, and then when you take the conjugate, then now you think this inner product as being here in the L phi space, and then you get this. And then after you're taking the bar again, you get the identity. Okay. So once they are equal, well, you know the formulas, and I think that's what I was trying to say in the beginning, which was a mistake at that moment. But once we know the formula for this guy and we know the formula for this guy in terms of phi and phi tilde, then you just realize that this identity implies that phi z minus phi tilde z must be some constant. Okay, because they have like phi tilde, so this is like phi, this is like phi w bar plus phi z divided by pi I w bar minus z. Okay, but this part here I can always cancel by this identity we just derived for the kernels, and then you just have this thing here, but then you just select one w, say I, and then you see that the difference must be a constant. It's simple to see. Okay, so what that implies is that, well, we do have a representation for these guys. So since that has to be a constant, then we go back and you make the difference of the kernels. So let's say k phi wz minus k phi tilde wz. Suppose, so let's assume that this constant is like c. So this would be 2c divided by pi I w bar minus z. Because this will be the sum of phi of z and a phi of w. Is this 0 or let me do this carefully. So this would be phi w bar plus phi z. Oh no, yeah, yes, but then it will be a difference. Okay, yes. So this is, oh yes, but there is a bar as well there. So that actually would be something like c bar plus c divided by pi I w bar minus z. Okay. Yes. But we do know that this also has this representation in terms of integrals, which is due to problem 5. So this is what? This would be p minus p tilde divided by pi, 1 over pi squared, integral from minus infinity to infinity of the mu minus mu tilde divided by t minus z and t minus w bar. Okay, where again, mu represents phi and mu tilde represents phi tilde. Okay, so then what you can do is a very simple thing. You can just multiply by w bar minus z, this whole thing, and then you will get that c bar plus c equals what? I w bar minus z p minus p tilde plus, or minus, let me write as a minus, 1 over pi I. And then this, once you multiply by w bar minus z, you can split this fraction in a difference of 2 t minus z. Yes, correct. And then the mu. So let me write here, maybe it's better to do nu as mu tilde, sorry, as mu minus mu tilde. Okay, so that would be the nu of t. Okay. And now what you can do is just you take a real part in this whole thing, and for, let's say, yes, okay, before I do take the real part to there, let me do another step. So you realize that now what you have is a function of w bar and a function of z, okay? And you have a difference of these two guys. okay, on this right-hand side. Okay, and the difference for any two things is a constant. So I have the difference of this guy minus this bit here. Okay, so then you realize that, okay, great. So that implies, so I can put any w, any z in this thing. That implies that 1 over pi I integral of the new t divided by t minus z is actually equal to some constant a, which I don't care, p tilde times z, okay? That implies that if I take this term together with this, is this p minus, make sure this, yeah, this is all right. So this is p here with minus, let's see if I'm writing this correctly. This is minus here with a plus there. Okay, so that has to be it. Okay. Oh no, probably this should be. This is z with the minus and this with the plus. Okay, yeah, that has to be it. Great. This is correct. Any questions here so far? Maybe I'm going fast in the computations, I don't know. Okay, great. So that's what we have. So what you can do is just you take real part on both sides, and you say take, so if you take, so say you take z equals iy, and then you take real part of everything, of both sides, and then you divide by y, okay? So if you do that, what you get in the end is that this part here will go to 0, but this I think is problem 4. And this part will converge, well, this guy will also converge to 0. And this guy will converge to this p minus p tilde, or maybe p tilde minus p. Anyway, so then p tilde minus p has to be 0. So this would imply, if you do this procedure, so this would imply that p equals p tilde, okay? So now we know that we can cancel this term here. So now you know that this is just a constant. But then again, you can use Poisson representation to realize, well, if that is the case, then if I take the real part on both sides, then you have just the convolution of the Poisson kernel against this measure here. And then by Poisson representation, we know that this measure has to give against the Poisson kernel has to be a constant. So this measure will have to be a constant, okay? So it's not easy, it is easy to see now by Poisson representation. Meaning the part where we take the limit back to the real line, that the nu of t has to be, let's say, constant equal to the real part of A. Okay. Yes, but what if that is true, then you can go back to what part? Let me see, part of A. Okay, so then that would imply, we have to continue a bit more. Well, this guy would just be then A plus some ID where these are real. Well, in particular, now you can go back. Now you can go back to what? Now you can go back to this bit here. Yes, now you can go back to this bit here. Yeah, this bit here. You know that this bit and this, guys, will give just a constant function. Okay, because we just derived that. Then you're taking a difference, so this bit will give 0. Okay, this guy is already 0. So then you conclude that C bar plus C is 0, meaning that the real part of C is 0. But C had to be real. Yeah, the real part of C is 0. So then you conclude that C is just a complex constant. So then you conclude that C is a complex. That C equals some I, let's say C naught for C real. Is that enough to conclude that phi equals phi tilde? Well, let's see. Well, they need to have real part. Yes. Complex constant. What else? Well, that's okay, because if this is a complex constant, yes, okay. So now actually, we should restate that actually. This is not true. This is sometimes I C naught in the reals. Okay, that's the statement, because if you realize, well, if you look at the kernel, if you had some complex constant, you would have some I C naught bar plus I C naught. That's what you would have. But then that cancels. Okay, so it could be the case if you take your phi and you add a complex constant that wouldn't change the fact that the real part is greater or equal than 0 in the upper half plane, but that would generate the exact same kernel. Okay, so that's the most we can ask. Okay. Great. Any questions in this remark? Okay, good. So basically, well, they define the same space. Because the important thing is if they define, well, the measures are the same. Now I should conclude that A is 0, no? If A is, now I have a question. I should conclude that A is 0, no? Let me see. The real part of the difference. Let's see. Too much. Yes. So this would be A, and this would be A. This would cancel. Oh no, I just concluded. Yes, I concluded that this A has to be yeah, that is, well, this A, if you take real part here on both sides, now this guy is 0, the real part, yes, I should, yeah, we just concluded that A has to be this guy, sorry, my mistake. We just computed this A has to be this guy here, because this A is this measure here. Therefore, if we do that, which is equal to that A will cancel. Wait, what's the important thing? Yeah, we concluded that C, I mean, we already know that C, okay, we already know, okay, I'm just got confused now, but anyway, we already know that the difference is a constant. The only thing I need to show that is the difference is a complex constant, and we just showed that. We don't need to show that A is 0. Okay. Okay. Any questions again? I got confused here in the end, but I think now it's good. Okay, so now I want to state the part 2 of the result. Okay, so this page 3. This is in page 1. So part 2. So part 2 is the following. Let TW be the following map. Okay. For some function in L phi. Okay, so we already know that L phi is well defined, Hilbert space, uniquely defined by phi, modulo adding a complex constant. And also a side remark is that, well, in the book, you will see that the Branges defines the space as function which are analytic in the upper half plane and the lower half plane, which I find a bit weird, but anyway, you can easily extend these functions to the lower half plane. It's just evaluate the function there. It's still well defined, everything. But I just find it a bit weird, but you will see that in the book. Anyway, continuing, define this operator TW. So the claim is then TW is continuous. In fact, you can even compute the norm of TW. In fact, we will show that the norm of TWF is less or equal than 1 over the imaginary part of W times norm of F. Of course, I'm doing this, so for each W here, for each W in the upper half plane, so I should say here, W in the upper half plane, okay? So even can compute the norm, great. And we have some identities, for instance, and we have some identities, let's say identity I, we have that the adjoint of TW is just TW bar. And we have some identity involving, if you take, let me use alpha beta, T beta star, and you divide, oops, and you divide this by alpha minus beta bar, then that is just T beta star T alpha. Okay. That's the other identity. And the final third identity is that if I consider the map U, so if I do U of f of x divided by x minus w, let's say, and I evaluate this in a point z, so this would be a function in the L phi space, that's exactly just TW of f of z. Okay. So it's basically about this operator TW. Okay, so let's prove it. Also pretty simple. So let's prove. Let's prove first that property 3, because if we prove property 3, then we do know that TW of f is a function in the space, because f of x divided by x minus w still is in L2 of mu, since w is in the upper half plane. So I will have no problem by dividing by this. It's actually, I'm just making things better, because then I'm dividing by something which is comparable to like 1 plus moduli of x. Okay, so let's prove 3. And then 3 is just a very simple thing, because if I do f of z minus fw divided by z minus w, then I know, again, I will assume that p equals 0 here. So, and I will leave you to fill the details for the other ones. But if I do this, then I know that this is just ft, the mu t, and then you have like 1 over t minus z minus 1 over t minus w, and then everything divided by z minus w. Okay? And if you do this, you realize that this is just 1 over pi I integral from minus infinity to infinity of what? You cancel the z minus w, so you have just the product. So then you can just move this t to the function. Okay, and then the mu t divided by t minus z, which is exactly, if you do this, this is exactly u of fx x minus w at a point z. Okay, so that shows identity 3, which also shows that t of w of f is also a function in the space. Okay, that to prove it's continuous, we will actually prove this inequality here, but to prove this inequality here is best to prove these 2 items first. Okay, so that was that was item I. So let me prove item I. Okay, so item, I should use a darker color. Yes, so how can we prove that? Well, that's also pretty simple, because we'll just take in a product. So what is FTWG? Well, by definition, you just go back to L2 mu and do the inner product there. And now I know that TWG is just u of this guy. So I know what function I have to go back to L2 of mu and do this inner product. So this would be exactly equal, by definition, ft, and then you have this guy, which would be gt divided by t minus w, but everything bar in the mu t. But then now you can just move this guy to below f, and you will see that that's exactly just tw bar f g. So therefore, the adjoint of tw is tw bar. Okay. What else? And then let's prove property 2. And actually, I will leave you as a thought exercise. If you actually have 2, then you have 1. Okay. But let's prove 2. But then 2 now is just trivially follows from 1, because T alpha minus T beta star is just T beta bar divided by alpha minus beta bar. And you just do you just take any function, apply this operator, and you do a computation, and you will see that that will be exactly as just composing this thing. And this is a simple computation. A simple. Just have to do some computations using this rational functions and taking differences, etc. And you will see that this identity holds. Okay. And then finally, let's show that it's continuous. Well, the way you show it's continuous is the following. So let's take, for instance, alpha equals beta equals W in this identity above. Oh, yes. Oh, yes, let's just take this. Yes. I think we don't even have to use 3. We can use only the first identity. So if I do this, then I get, let's say, F T. No, sorry, I have to use the other one, which is this identity here. So let me use this identity. Yes, I do have to use that. W minus TW bar divided by W minus W bar, and apply this to a function F. And then I take the inner product against a function G. Okay, that's what we have. But we do know that this equals, by the identity we just showed, to TW bar, TW, FG. Okay, but then I move the TW to the other, to G, because I know the TW bar is just TW joint. So this is just TWF, TWG. Okay, then if F equals G, then you get an identity. We can also work out what's going on here, and it's a simple computation as well. Then you realize that the imaginary part of TWF F equals the imaginary part of W times the norm of TW F squared. Okay, and this bit here, together with this bit, just comes from this term here, and this term here just comes from this guy here. Once you put F equals G. Okay, so now you can just apply the Cauchy-Schwarz inequality, and you will see that the imaginary part of W, norm of TWF squared, is less or equal than TF times the norm of F. Okay, then you can cancel both the two norms. So then you conclude that this is less or equal than 1 over the imaginary part of W, norm of F. Okay, and therefore it's continuous. And that finishes the result. Okay. Any questions here in this second part? Okay, so in this last 20 minutes, I will show the converse of this result, which is really the nice part. And you will see the same thing when we define the Branges spaces as the L-phi spaces. In the Branges spaces case, I will start with a certain function E, and then I would define the Branges space associated with this function, and it would satisfy three conditions. And then if I have any space which satisfies these three conditions, then it has to be given by this function E. It's exactly like here, we have this function phi, we create a space, but what if I have a space L, which I don't know if it's given by some L phi. So suppose I have some space L, which I don't know if it's given by some L phi, but I know that this guy has some properties that make it look like an L phi. Then I will actually conclude is an L phi, okay? So if I have a space L with certain properties, I should conclude that is a L phi. That's the idea. So this is theorem 6. Okay, so what's theorem 6? So let L be a Hilbert space of analytic functions say f from C plus to C, so that we have three conditions. First condition, there exists some W naught in the hyperplane plane, just one guy, so that this map, this evaluation map, but just for this single W naught is continuous. We will end up showing that, in fact, it will be continuous for everything, for every W, but anyway, you just need one. 2, that the operator T I just defined, TW belongs to L for every F in L and W in the upper half plane. And 3, do I have to assume that's for every W? Maybe I don't. Let me see. Yes, has to be for every. And 3, we have that mysterious identity. For every alpha and beta in the upper half plane. Okay, then there exists some phi. Again, a phi which has a positive, no negative real part in the upper half plane, so that L equals L phi isometrically. Okay. And are not just the same as a set, but it has the same structure. So it has the same, which is to say they have the same inner product, or which is to say they have the same norm. Okay, so that's the nice thing. Whenever you have a certain space L which has properties that look like they should be an L phi, then the answer is that yes, it is a L phi. Proof. Okay, the proof is not long. Okay, so but what I just said, one can show, and I will leave that as an exercise, can show, but I won't need that now, but in a moment. Okay, okay. So what I want to do is the following. So let me use identity tree. So by 3, what do we have? I want to show that TW is continuous, okay? I want to use that TW is continuous to say that then property 1, so I want to prove that TW is continuous. Then I will use that to say that, well, actually, the evaluation map is continuous for every W naught you take in the upper half plane, not just for this one. Okay. And then once I have this, then this would allow me, so the space we have a continuous functional, evaluation functional, that would imply by Rie's representation theorem, which works in every Hilbert space, that any continuous functional is given by the inner product against some function, and you define that function to be the reproducing kernel. Then you would have a reproducing kernel, and then you use this identity again to extract from the reproducing kernel your function phi. Yeah, that's more or less the idea of the proof. So first I have to show that TW is continuous. So by 3, what do we have? So let me kind of redo the proof I just did. So suppose we have, let's say, TW, let's say alpha minus T alpha star divided by alpha minus alpha bar. So I'm using beta equals alpha here, and I put F against F. And I know by this identity, this is just T alpha star, T alpha, F against F. And basically by the same computations, I just move the same thing I did before. I just move this guy to this, and then you get the norm of T alpha squared. And then you just work out what this is, because then I can move this guy to that part, and it will be exactly the same thing. So you will conclude that the imaginary part of T alpha F. What I'm trying to say is I don't really need to know that T alpha star equals T alpha bar to prove that T alpha is continuous. Oh, this is alpha. Squared then by the Cauchy inequality. Again, we can show that T alpha F is less or equal than 1 over imaginary part of alpha F. So T alpha, so the operator T alpha is bounded or continuous. Okay? Basically the same computation. Great. But then now what you can do, you do the following trick. Well, if I want to prove that the functional that takes F and maps to FW, but now for every W is continuous, what I just do, I do the following trick. Take that W naught, which I know it works, and I use this T alpha to help me out. So FW is actually another function, which is this function here inside, evaluated at W naught. Because if you just put Z equals W naught here, then this part here will cancel with this. Then you have FW naught here, and is this in the right order? Maybe it should be plus. Then you have minus with minus, this would be, oh, this would be W, and Z would be W naught, yes. So this would be W naught, and this would be W naught, so they will cancel. This part will cancel with that, and we just have this, which is F of W. Okay, but this is what? This is just F minus W naught minus W, TW, this evaluated at Z equals W naught. Well, but as we assume that this evaluation of functional was continuous. So this part here of the evaluation will be a continuous functional. And this is just, I'm taking a function here given by a continuous map and evaluating again at W naught. So this I'm composing TW which is continuous, with the evaluation of functional at W naught. So therefore, this part here should also be continuous by the hypothesis. So FW, so F that maps FW is a continuous function. For every W, okay? And that comes by the continuity of TW. Okay, any questions here in this computation? Great, so now, what do we have? Okay, so now we know that the functional is continuous, evaluation of functional is continuous for every W in the upper half plane. So that means that, so by Ree's representation, and I will say what Ree's representation is, which is whenever you have a continuous functional, then it must be represented by the inner product against a vector in the space. So therefore, there exists some kernel KWZ, which I also write as KWZ, such that this is true as an inner product in the space L. Okay. So we do know that the space should be an L phi. And so the KW should be by that weird formula. So we are aiming, so maybe I should write here. We are aiming to show that this thing is of this form. Okay, that's our aim. So somehow I have to, from KWZ, I have to extract this FW information here. So you think that, well, if I multiply my KWZ by pi I WZ minus Z, then I will get FZ modulo a constant. Okay, so if I make that constant in a way that is purely complex, as we saw before, then it shouldn't be a problem. I should be able to recover phi by the kernel once I multiply by this. So that's the idea. And for that, we use identity 3 again. So we use condition 3. Okay, so let me use that. So, oh, now I have to use, and I will be to put that as an exercise. So let's say exercise. Show T alpha star is actually T alpha bar from I. Or is I no, it's from 3. Sorry, from condition 3. So from this guy here, you can show that the adjoint is just taking bars, okay? Okay, so once I know this, then I can do F, let's say T beta K alpha. Let me put, yes, T beta K alpha. So I'm applying T beta in the K alpha kernel. Okay, well, I do know that this will be then T beta star F K alpha. Okay, but this is the reproducing kernel. So this is just T beta star f of alpha, which I can write what it is. It's just f of alpha minus, well, I know what T beta star is now because T beta star by the exercise is just T beta bar. So this would just be that. Okay. But then I can also write what this is. This is just f k alpha minus k beta bar divided by alpha bar minus beta in a product in the space, because I know that k is a reproducing kernel. So this identity here, if this equals that, works for every f. So therefore, this function here and this one must be identical because it works for every function in the space. So T beta K alpha Z should be K alpha Z minus K beta bar Z divided by alpha bar beta. Okay, another thing you can show, and this works for every reproducing kernel, is that K, let's say alpha beta bar, if you do bar in everything, is just K beta alpha. And that is a simple computation because K, well, another way of saying is this, which K alpha beta is just by definition K alpha in a product with K beta, but that is just K beta in a product with K alpha everything bar. So, but that is just K beta alpha bar. Okay, so that we always have. So then if you use these two identities, let me write what this other identity is explicitly. Let me write what this guy here is explicitly. This guy here is what? This guy is K alpha Z minus K alpha beta divided by Z minus beta equals that. Great. So then now you can use this plus this. So let's say, yes, let's say this plus 2 points, this. So using this plus these 2 points, okay, we can deduce. Again, there is a computation to be made here, which I'm omitting. It's simple. We can deduce that pi I alpha bar minus Z K alpha Z equals pi I alpha bar minus beta K alpha beta plus pi I beta minus Z K beta bar Z. Okay, and that's really the identity we need, because we have a guess. We have a guess how to define phi, and this is the guess. So now define phi this way. So what I did was remember that we have these insights. Well, that was what was in our mind. So I just take a certain W, which I'm calling alpha in this case, and then multiplying KWZ by this alpha, by alpha minus Z. And so in this case, I'm calling alpha naught. Yes, alpha naught minus Z. So I'm taking that with alpha naught bar. So that's why we have alpha 0 bar here. So basically that's what we're doing. We're taking this guy here equals alpha 0. This guy equals alpha 0 bar, sorry. For some alpha 0 in the upper half plane, I don't care. And then multiplying this part here. And then we get this guy with phi of, let's say, bar alpha 0 bar, you have to take care of this constant. And the way to take care of this constant is to add a certain constant, which will be this one. And you note that this is nice because this here is purely complex and has negative, so this guy here is something like minus I some c. So when I multiply by this I get some positive number here. Oh, this is supposed to be alpha 0, sorry. Alpha 0. And this thing is positive. Why? Because, well, because k alpha 0, recall that this thing here equals the inner product of k alpha 0 with k alpha 0, which is just the norm of k alpha 0, which is greater or equal than 0. So this whole thing here, maybe I should put in green. This whole thing here is greater or equal than 0. Am I saying the right things? I think so. Yes, this whole thing is greater or equal. So what I'm just doing, I'm fixing that constant by adding some positive number, so I don't screw up with the positivity of the real part. But other than this linear factor, I'm basically just doing what I said before, just multiplying this by the kernel. Okay, and then you can use, so then using, let's say 3 points. So using we can show, well, I'm already over time, but maybe you can give me like, I can finish in 5 minutes, I guess. We can show that KWZ okay. So now, great, you just decomposed your kernel in the shape you wanted. This thing I just said is positive. So once we take the real part, so once you have this, then you just do KWW, which we know is greater or equal than 0 by the same comment. But this guy now equals, by the formula, just equals to the real part of f of w divided by what? Pi times the imaginary part of w. So you know that the real part of f is greater or equal than 0 in the path plane. Great, awesome. Just got our function. Now we have to finish. How do we finish? So now we define, so we can so we can define L phi nicely, and we realize that, and we note that L phi and L have the same kernel. In particular, if one, we consider the span of the functions kw, which will be functions in both spaces because they have the same kernel. Okay, so just take linear combinations of kW's with some w's in the upper half plane. Okay, this thing, and what we leave as an exercise, is dense in L phi or L. Well, they are both functions in L, and they are both be dense in the norm of L phi and in the norm of L. Okay, so why is that the case? Because, well, you can represent any function as a inner product against f of w is the inner product against kw. So then if you use that and you assume that this thing is not dense, then that would imply that there is a function in the space that it's the inner product against kw, every kw is zero. So therefore the function has to be zero. Okay, so that's why it's dense. And so this is easy to show as well. And the second thing that it's the norm, since you're going to take, if you want to evaluate norms of linear combinations of these things or inner products, well, it just, in the end, it's just inner products of kernels or norms of kernels, but the kernels are the same. So you're going to get the same answers. So you realize that the norm of L and the norm of L phi coincide in this span of the kWs. Okay. So therefore, L phi is the closure of this span with a certain norm, but it's the same thing, but it has the same norm. If you use another norm and you take the closure with this other norm, then you get L phi. If you take with this norm, then you get L. But you're taking the closure of the very same set with the very same norm, so you have to get the same space. So therefore, L phi equals L. Okay, and that finishes the proof. Okay. Any questions in this final part? Okay, if we don't have any more questions, then I will stop the recording. Okay, thank you.